So good morning.
Good morning.
Shared documents. I think last time we were talking about the general uniform linear arrays, and we say that these arrays are usually fed either by equal amplitude currents with a phase shift that is progressive down the elements, or they could be fed conditions for which we'll have an end fire array or a broadside array. Now, what we want to look at is continue with that discussion. And we'll look at the nulls for whatever the nulls in the locations for the phi are different in both the broadside and the end fire cases because of the different excitation conditions that you are dealing with. So if psi naught is not 1 is the value for psi at which the array factor attains its first nulls, then we can write that n multiplied by that psi naught 1 by 2 will be equal to plus or minus pi, giving us a value of psi naught 1 of plus or minus twice pi by n. And for a broadside array, we would get an alpha equal to 0, so that psi naught is equal to phi naught is equal to pi by 2, and hence psi would be just simply given by the electrical length kd and multiplied by the cosine of phi, and in this case. And then if the first nulls will occur at phi 0, 1, the beam width between the first nulls, that is dWFN, is going to be given by twice delta phi equal to twice into phi naught 1 minus phi naught. Now at phi naught 1, the cosine of phi naught 1 is going to be given by the cosine of phi naught plus the half the bandwidth. And this will give us a value of psi naught 1 over kd. And with phi naught equal to pi by 2, then we can expand that in a trigonometric function, and we get a value of the minus of sine delta phi equal to the minus of twice pi by n multiplied by kd. And if the length of the array is very long compared to the wavelength, that is, the number of elements we have are large, then we can see that delta phi is just going to be given by this arc sine of twice pi by n kd, which can be approximated by the argument lambda by nd, okay? When that value is large, that is nd is large, then we can get a value of lambda by nd in radians. So we see that the bandwidth is going to be just proportional to the ratio, the inverse ratio of the length of the total length of the array by the wavelength. So for an end-fire array, we saw that alpha has to be given by the minus of kd, and therefore phi naught is going to be equal to 0. And in this case, we have that psi is going to be given by kd multiplied by the cosine of phi and minus 1, giving us a value of cosine of phi naught minus 1 equal to sine naught 1 by kd, or a value of minus lambda by nd. And since the cosine of phi naught 1 is equal to cos phi naught plus delta phi, then you can see that the cosine of delta phi is just going to be given by the square root of 1 minus sine squared of delta phi. Or in other words, we can get a value for cosine of phi naught 1 equal to 1 minus a half of delta phi all squared, when delta phi is small. And therefore, we can use binomial expansion of that particular equation. And thus, we see that the half the delta phi squared is equal to the lambda, that is the wavelength, divided by the length of the array, or in other words, the delta phi is just the square root of twice the ratio of the wavelength to the length of the array. So we conclude, therefore, that the end-fire array will have a wider beamwidth than that of the broadside one. That is, the broadside has a sharper beam than the end-fire one. So the uniform array, linear array, has side lobes that will occur whenever the denominator in the array factor is equal to unity. That is, sine n phi by 2, psi by 2 is equal to unity. Or in other words, n psi by 2 is equal to twice n plus 1 pi by 2. That is odd multiples of pi by 2. And the first side lobe will therefore occur at n equal to n psi by 2 equal to plus or minus 3 by 2 pi. So the level of the first side lobes, okay, relative to the main lobe, is therefore going to be given by 1 over n 1 over sine 3 by 2n pi, giving us a value of approximately 2 by 3 pi, which is about 13.5 dB whenever n is large. And hence, when the number of elements in the array is large, the first side lobes will be down 13.5 dB from the principal maximum, independent of the value of n. But remember, n must be large for you to make that kind of assumption. So the side lobes can be suppressed by exciting the center elements with higher current than those toward the array. And that is, we are tapering the excitation current to the elements. So example 3, a broadside array of 5 isotropic elements spaced at distance d equal to lambda by 2 apart is excited by currents in the ratio of 1 to 2 to 3 to 2 to 1. That is the binomial kind of distribution. Not binomial, but the Pascal's triangle, we remember, our binomial distribution, of course. So we are required to determine the normalized radiation pattern of the array and compare the level of the first side lobes with those of a 5-element uniform array. So we have that the array factor A of psi is going to be given by 1/9 into 1 plus 2 by exponent of that. That is, we are feeding in the currents. Remember, we saw that this was going to be given by the sum of the exponent, okay, of the J psi in powers. And we get a value of about 1/9 into twice cosine twice psi plus 4 cosine phi plus 3. So we divide by the sum of the currents so that we normalize the array factor to unity. We remember the current is not uniform. That's why we are not using the 5 elements here, but we are using the total value of the current, which is about 9, so to speak. And therefore, psi kd of cosine phi plus alpha is equal to pi cosine of phi, and alpha is therefore equal to 0, and d is equal to lambda by 2. So the normalized radiation pattern may be plotted from A of phi equal to 1/9 into twice cosine of twice pi cosine phi plus 4 cosine pi multiplied by cosine of phi, that is pi cosine phi plus 3. But we note that because we have already plotted A of phi, we need not recalculate the array function. We have already plotted psi, that is A psi, and we cannot, we don't need to plot it again or recalculate the array factor as a function of phi. And therefore, what we do is that we can plot that from that of A psi graphically by doing the following case. This is the plot that we already plotted for A of psi before. That is, we can use the function for A of psi and then plot it, and this is what we'll get. And now what we do is that below it, centered at the axis, the A psi magnitude axis, we can draw a circle, okay, with the radius of P1, P2, and then we can then plot the values of the whatever, just reading off from the different points of the on the A psi plot. We can therefore plot this whatever the variation with respect to phi. That is phi and that is psi. So to obtain A of phi from A of psi, what we need to do is to extend the vertical axis from the array factor graph to intersect with a horizontal line that represents the phi equal to 0 and phi equal to pi line as shown, and the intersection point is for the case where alpha is equal to 0. Then we locate a point P0 on this line, that is alpha radians to the right or left of the intersection point, depending on the sign of alpha. That is, if you look at that, we have the P0, which is the case of alpha. Then, depending on the alpha that we have, we can draw either P1 or P2 here, okay, to get a value of the sign, considering the sign of the alpha, which is the phase shift of the excitation current. So for the case of alpha equal to 0, okay, then P0 will be the intersection point in this particular case. So we use the P0 as the center, and we draw a circle of radius equal to KD, that is the electrical length of the separation. And for any angle phi 1, we can therefore draw the radius vector P0 P1 and project P1 to P1 prime on the horizontal axis. That is, you draw a radius with the vector P0 P1, and then you project it down, and the projection will have a value of psi 1 equal to KD and the cosine multiplied by the cosine of phi 1. And then we can measure, that is at phi 1, psi 1, we measure the value of the magnitude of the array factor and mark it as P2 on the radius vector P0, P1. And P2 is therefore a point on the normalized radiation pattern. And we repeat the procedure to obtain the complete pattern, which we saw was at figure 8 for the uniform array. So tapering the excitation on the array has a desirable effect of suppressing the side lobes. That is where we are feeding the center elements with a higher currents than the end elements. This can alternatively be achieved when we use an ununiform element spacing. Just like when you are designing filters in third year, where you left some of the poles on the unit circle in the S-plane, you left some of the poles, and therefore you are able to get a value, a different kind of transfer function for the filter. So the same thing, we can use this similar technique and remove some of the elements from the array itself, so thereby making the inter-element spacing in a uniform throughout the array. So we can vary the current facing as well, and varying alpha from 0 to minus kb, the main lobe can be directed from a broadside for alpha equal to 0 to an end fire kind of beam for alpha equal to minus kb. Now remember, we can electronically accomplish the phase shifting of the current when scanning the array, and therefore the array becomes what we call a phased array, a phased array, so to speak. So in 2D arrays, the scanning in both theta and phi is as well possible, and this becomes useful in applications that will require large arrays. So for example, what we were talking about, the 5G radio, the antennas will be scanning. That is, you can change the direction of the beam by just using electronic phasing of the currents that are exciting the elements in the antenna array. And it was also used in scanning radar, or in whatever, in airports, for directing the beams towards the targets. Before the advent of the phased arrays, you needed to physically rotate the antenna, and if you went to airports of an earlier years, you'd get a big rotating radar antenna on top of the buildings, and it will be mechanically rotated so that it can point at different regions of the sky. But with electronic scanning, all you now have to do is just to change the phases, and the beam will be shifted in the direction in which it's pointing at the sky. So the phase control can be done using time delay circuits, in which a varying frequency is transformed into a phase shift by the time delay circuit. And in this case, we'll then call this a frequency scanning. Remember, frequency and phase are the same, only that the frequency is the derivative of time derivative of phase, while the phase is an integral of the frequency. Okay, so they are related things, and therefore we can either use actual phase, or we can use the rate of change of the phase to do the scanning. And that brings us to the end of that particular section of the array systems. This is as far as we'll go about array designs or array topics, and anybody with questions can now ask. If there are no questions, I'll go to the next topic, which is about the receiving antenna. So we have maybe a minute to decide to think about what we have just talked about, and see whether we have any clarification required, or if there is none, I will then propose I continue. Okay, fine. Since there are no questions, then I look at a receiving antenna. But what we can say is that the receiving antenna and the transmission antenna will have the same properties from what we talked about last semester about the reciprocity principle. So the incident field that is falling will be falling on the entire antenna when it is operated in the receiving mode. And this will induce electric currents on the structure itself. So the induced currents and the charges will depend on the angle of arrival, which is usually abbreviated as A or A of the incident wave, and will produce the radiation or scattering. So this then implies that the current and charge distributions on an antenna are going to be different when the antenna is operated in the receiving or the transmitting mode. But reciprocity arguments lead us to to see that there's equivalence in the source impedance in receiving and transmitting modes. That is, the impedance will have equal magnitudes when the antennas are identical. That is, if the receiving antenna and the transmitting antenna are actually identical, then we can see that their input impedance or source impedance are going to be the same. So the identical direction patterns of the antenna, that is the antenna patterns, radiation patterns in receiving and transmitting modes will be the same. And therefore we consider two identical antennas, antenna A operated in the transmitting mode and antenna B operated in a receiving mode. And antenna B is positioned with respect to the center line or the axis, is rotated over a fixed radius r about centered at the transmitting antenna. And the distance r is assumed to be much larger than the wavelength of the signal that is being operated, the antenna is transmitting. So we assume antenna A transmits electromagnetic energy toward the receiving antenna B, which absorbs it completely. That is, there's no scattering. That is, it just absorbs all the energy transmitted by A. So then B is rotated about B at a constant radius r, while keeping its orientation with respect to A such that we have perfect polarization match between the two antennas. Remember, we said when we were talking about the equivalent length of an antenna for a receiving antenna, we said that if the incident wave and the antenna surface or the receiving surfaces are not matched phase, we'll have to use a dot, that is the cosine of the angle between the electric field vector and the direction vector of that antenna. That is the orientation of the antenna, and therefore the field is going to be 0. So all we are saying is that the antenna A and B will always be arranged such that the maximum power is absorbed by B all the time. So the system can therefore be represented as a two-port T network as shown below, where we have the series arm impedance, which you used ZA. I think you used ZA, ZB, and ZC when you are dealing with filters. All I'm using is that I'm using the Z parameters of the network, and therefore defining the ZA and ZB as Z11 minus Z12, where Z11 is of course the driving point impedance of the two-port network with the output port short-circuited, less the reverse impedance, the transfer impedance, plus, and the ZB here is Z22 and a Z12, and therefore the Z12, of course, is that of the or the mutual impedance, or the transfer impedance, so to speak. So this, of course, already has invoked the idea that the two-port network we are dealing with is a reciprocal network, and therefore in the reciprocal network, you remember the Z21, that is the forward transfer impedance, and the backward reverse transfer impedance are equal for such kind of systems. And therefore, I'm just replacing the Z21 and Z12 with just one single impedance here. So V1 and V2 are, of course, the output and input voltages at the ports, and ZL is the terminating load. Now, we therefore can write that the V1, V2 can be given by the impedance matrix multiplying the input and output currents I1 and I2. I guess in the diagram I've forgotten to label the currents. I'll correct this. So for a bilateral intervening medium, that is, we know that the antenna A and antenna B are spatially separated, and in between we have a medium, either free space or it could be filled with dielectric or something. But as long as it's bilateral, that it conducts, or the properties do not depend on the direction, then the reciprocity will hold, and therefore we can have that Z21 is equal to Z12. So the coupling impedance Z12 and Z21 may be expected to be very small in this system because R is very large by assumption. And this will be justified because the reaction of A to the scattered field from B will be negligible in this case. So in the limit, as we take R to infinity, the Z12 must go to 0. So the common arm of the T network will therefore be very nearly a short circuit, and Z11 and Z22 will also be very close to the input impedances of the antenna A and B, and this we represent by ZA for antenna A and ZB for antenna B when they are operated in isolation. That is, they are not close together. And we can therefore write that V1 will be approximately given by I1 Z11, which is equal to approximately ZI1 multiplied by ZA. And because the field at B is due to radiated energy from A, we can, however, not ignore the forward transfer impedance Z21, however small it is. So we can modify the T network into an equivalent Thevenin source and source impedance driving at load impedance ZL representing the antenna B. That is, we have the open circuit voltage of the Thevenin source, its source impedance given by ZG, which for generator, and the load itself out there, and this is the voltage at the output of the T network, that is V2. And here we therefore have that V open circuit is going to be given by the reverse transfer impedance N12 V1 over Z12 plus Z11 minus Z12, which is approximately Z12 over Z11 V1. This obtained from the T network that we already have before when we are dividing, or when we are making the value. That is, we'll apply Thevenin's theorem to this value here, to this impedance, or to this network. You apply the Thevenin's, that is, open circuit the output port, look into the output port and get the value of the impedance that you see when you're looking into the port, and then you get the voltage that will be seen at this point, which will just be given by the, whatever the voltage at this point, okay, given by that value. Because it's open circuit, there will be no current flowing, and therefore this impedance does not matter, and we just have the potential divider impedance, which is Z12 plus Z11 minus Z12 there. So that's what we have done here for the equivalent circuit. And ZG is of course going to be given by Z11 minus Z12, which will be in parallel with Z12 and adding a series value of Z22 minus Z11, because when you are looking for the impedance, the equivalent source impedance for the Thevenin circuit is you reduce all the forcing sources to their equivalent internal impedances for a good voltage source. Of course, the impedance is going to be a short circuit, and therefore you just have Z11 minus Z12 being in parallel with Z12 and in series with that output amp, and we get a value of Z22, which is minus Z12 all squared over Z11. So the equivalent Thevenin source impedance Zg for the antenna B in the receiving mode is therefore going to be approximately its input impedance Zb, okay, when it's operated in its transmitting mode. And this is because we have assumed very weak coupling between the two antennas. And therefore, Zg will be approximately Z22, which is approximately Zb. So in receiving mode, therefore, we can write that the B2 voltage is going to be given by the minus of I2 multiplied by the load impedance, where we are using minus I2 because of the definition of the positive I2 flow. And this is gives us a value of I2 equal to the minus of Z21 over Z22 plus ZL, and multiplied by the input current I1. Remember, in two-port network analysis, all the currents are assumed to be flowing into the ports. So the time average power absorbed in ZL will then be given by PL equal to a half the real part of the minus of V2 multiplied by I2 conjugate. And this gives us a value of I1 squared by 2 multiplied by Z21 over Z22 plus ZL all squared multiplied by the real part of the load. So at two successive points of B, say the point 1 and 2, where we have shown that point 1 is on the axis, and then 2 is the rotated position from the diagram that we showed before. I find it a little bit cumbersome to keep on going back to the diagram. Then the ratio of the absorbed power in ZL is going to be given by the power at the original location, theta 1 phi 1, over the power absorbed in the load at the new location, and this will be given by the coupling impedance Z21 at the old position and divided by that at the new position, all squared. From the reciprocity theorem, the same power will be absorbed at A with B transmitting and A receiving. That is, we have calculated this assuming that B is receiving and A is transmitting. And since A and B are identical, then we can compute the same value when we make B to transmit and A to receive. And hence, the directional patterns or the direction patterns of an antenna or the radiation pattern of an antenna in the receiving or transmitting modes must be identical. So, receiving antennas are conveniently described using an effective area or aperture or receiving cross-section. So for a receiving antenna, the effective aperture is the ratio of the time average power delivered to the matched load to the time average pointing vector incident on the antenna. And it's possible the receiving the effective area or aperture of the antenna is going to be different from the physical dimensions of the antenna itself. So if we let A of E be the effective aperture of a receiving antenna, then we can write this from the definition here that the power absorbed in the receiving antenna PL is going to be given by its effective aperture multiplied by the average power that is incident on it, which is P average. And PL is therefore the maximum time average power absorbed in the matched load with the antenna oriented in the appropriate way with respect to the polarization of the incident wave. So if we assume the load is matched to the input impedance ZB of the antenna, then we can write that ZL is going to be given by ZB conjugate, and this will be given by RB minus JXB, where RB, of course, is the real part of ZB, and the XB is the real part of ZB as well. So the maximum average power then delivered to the load is going to be given by PL equal to I1 multiplied by Z21 all squared and taking the magnitude over 8 RB. Remember, because when we add at the bottom the value, that is the value of ZL plus ZB, we'll get only a real part remaining. And since we have also another 2, and we are going to be squaring the magnitude squared of ZL plus ZB, we'll get an 8 there. That's where the 8 is coming from. So if ZA is equal to RA plus JXA, that is the input impedance of the transmitting antenna is ZA, the average transmitted power is going to be given by PT equal to I1 squared over 2 and multiplied by the real part of that impedance. And hence, we can see that the absorbed power by the receiving antenna over the transmitted power is just going to be given by the forward transfer impedance, magnitude squared over 4 multiplied by the real part of the impedance of ZA and the impedance of antenna B. So the time average pointing vector at the receiving antenna will depend on the directive gain of the transmitting antenna in the direction of that of the receiving one. And therefore, we can write that P average is just going to be given by P of T over 4 pi R squared, that is the transmitted power assumed to be transmitted equally in all directions. Therefore, we divide it by the surface area of the spherical volume enclosing the antenna A, and we multiply that one by the directive gain of that antenna, which we are calling GDA. Hence, the power received by antenna B will be given by its effective aperture multiplied by the transmitted or the average power at B, average incident power at B. And therefore, we can see that PL by PT is therefore going to be given by the effective aperture of antenna B multiplied by the value of G, that is the directive gain of antenna A, and divided by the surface area. And we get a value of that magnitude divided by 4RA RB. And we therefore note that the magnitude of the forward transfer impedance is just simply the real parts of the impedances of the antenna multiplied by the effective aperture of antenna B, the directive gain of antenna A, and divided by pi R squared. So if B is used to transmit while A receives, then we would have equivalently a value of Z21 or Z12, if you like, all squared equal to RA at B, the effective aperture of A over pi R squared multiplied by the directive gain of antenna B, and we'll get a value of that nature as well. So this is 1 to rather. And thus, we can see that the ratio of the directive gain to the effective aperture for antenna A and is equal to that of antenna B, because we say that these antennas are identical. So we can say in words that the ratio of the directive gain to effective aperture of an antenna is a universal constant. Okay, we haven't said anything about these values. Therefore, it's a universal constant since the type of the two antennas is not specified. It could be a magnetic loop, could be a Hertzian dipole, it could be a thin wire dipole, and so forth. Okay, we haven't defined what these ones are or what the antenna were, and they are in deriving these ratios. Okay, and the only thing we required there was that the antennas be identical. So this is a universal ratio and it will become very useful for you in analyzing antennas. So example, determine the effective aperture of a Hertzian dipole of length L much smaller than lambda, that is the wavelength, used to receive an incident plane wave of wavelength lambda polarized parallel to the plane of incidence. Now, this is polarization is from the last semester cases, and I noticed that most of us, of course, we either cram or we don't put a lot of thought when you are given information in a given question. That is, we have been told that the incident wave is polarized parallel to the plane of incidence, and therefore it means that the vector of the electric field intensity is in the same plane as the direction, that is the unit normal, outward normal at the interface, as well as the direction of propagation vector. So we are told to, we'll let that the incident electric field be given by the modulus of that incident wave electric field in the wave at the dipole. So the time average power density at the pole, at the dipole, is therefore going to be given by P average equal to a half of EI squared divided by the intrinsic impedance of the intervening medium. So the average power delivered to a matched load, ZL equal to ZG star, is therefore going to be given by PL equal to a half multiplied by the voltage induced in the antenna, which is just the electric field intensity multiplied by the length, that is the length of the antenna. And remember, we are looking for the component of E that is parallel to the antenna orientation, and we therefore use the sine of theta over Zg plus Zg star, and multiplied by the radiation resistance RR, and we get a value of EIN over 8 R all squared, and multiplied by sine squared theta. And remember that for the Hertzian dipole, we saw that RR was just simply given by 80 pi squared into L over lambda all squared. And hence, PL divided by P average is going to give us the effective aperture of that antenna, and we get a value of eta over 4 R squared, I squared, sine theta, L squared, sine theta squared, and this gives us a value of 3 by 8 pi multiplied by lambda sine theta. And this gives us a value of lambda squared by 4 pi and multiplied by the 3 by 2 sine squared theta. Recall that this value here we already saw before when we were looking at the dipole. And this we see it's no longer dependent on the length of the dipole itself. But remember, for us to get this value, we had to assume that L was much smaller than lambda. Therefore, for antennas for which their lengths are much smaller than the operating wavelength, then this would be the expression for the ratio or for the effective aperture of the antenna. So for a Hertzian dipole, we can see that the directive gain is just going to be given by 3 by 2 sine squared theta. And hence, the effective aperture of the Hertzian dipole is just going to be given by lambda squared, that is wavelength squared, divided by 4 pi and multiplied by the directive gain of the Hertzian dipole. And for thin linear antennas, the definition of effective aperture is a little bit arbitrary, but is still useful in measuring what the available power at the antenna would be. So we can expect the effective aperture to be proportional to the effective length LE theta for such kind of antennas. Remember, the thin antennas, linear antennas we are talking about are either the half-wave lambda dipole or the quarter-wave monopole and so forth. And therefore, we can write that PL is going to be given by the open circuit voltage induced at the terminals divided by 8R multiplied by the radiation resistance, and we get a value of the minus of EI LE, or that is effective length divided by 8R there. And hence, the effective aperture is going to be given by a value of 30 pi divided by the radiation resistance and multiplied by the effective length squared in the direction theta. So we now look at what we call backscatter cross-section, because in many cases for us, for those of us who will be working with KBF or working with the civil aviation, we'll be using electromagnetic waves launched into the sky towards an object by an antenna, and then we expect or we wait for the echo to come back and we receive that. Okay? So the object must be able to scatter the incident electromagnetic wave on them. Of course, even for those of us who will be working in the meteorological department, this is the way you'll be detecting rain clouds or storm clouds and so forth. So it is often convenient to express the scattered field in terms of the backscatter or radiation or radar cross-section. Remember, scattering is the same as reflection from the object, only that we are not talking about specular reflection, where the angle of incident is equal to the angle of reflection, okay? But we are talking about an object that will reflect the energy in all sorts of directions. That is diffuse kind of radiation. So the radar cross-section is therefore equivalent to the cross-section that would intercept the same power as the incident power to produce the same amount of scattered power at the receiver when the scattering, this power is, that is the scattered power is isotropically, in an isotropical manner, that is isotropic manner. So we let Pi be the time average power density that is incident on the scatterer or the object we are talking about. So PS will be the time average power density that is scattered by the object and measured at the receiver. So sigma BS will be the backscatter cross-section, that is the effective aperture of the object that is doing the scattering. Remember, when it's scattered and we receive it at our position, we are using the scatterer as an antenna. It's transmitting that energy back to us. So R is going to be assumed, that is the scatterer is assumed to be a distance R from the receiver that is much larger than the operating frequency. And hence, that is wavelength. Hence, the PS received at the receiver will be given by this backscatter cross-section of the object multiplied by the power incident on it divided by 4 pi r squared. That is, we are assuming it's scattering isotropically of a spherical surface centered at the scattering object. And therefore, you can see the backscatter cross-section can be given simply by 4 pi r squared multiplied by the ratio of the received power over the incident power at the scatterer. And since PS will be varying as 1 by r squared, okay, over the distance, then the backscatter cross-section will be independent of r. So the backscatter cross-section is a measure of the detectability of an object or a target or a radar system. And therefore, in the military, when you want to, you have heard of planes called stealth bombers and the likes. The idea is that you make the object not have smooth surfaces, but rough surfaces with all angles, so that when you shine an electromagnetic on the object, it scatters that energy in all directions, such that the PS that you receive at the receiving antenna is so small that you won't know whether that plane is there or not, or it could be a bird or something like that. So the radar system will not be able to detect it as an enemy, kind of jet fighter, so to speak. So sigma BS, that is the backscatter cross section, will depend on the geometry of the object, the orientation and constitutive parameters of that object. We can make the constitutive parameters of the object to be absorptive, that is, it's matched to the intervening intrinsic impedance of the medium, and therefore all the energy incident of it is absorbed and therefore not scattered back to you, and therefore you won't be able to detect that particular object. And two, the frequency and the polarization of the incident wave. And therefore, we look at another example of the using the backscatter cross section. So a uniform plane wave with an incident electric field intensity EI directed in the Z direction illuminates a small dielectric sphere of radius B much smaller than lambda, that is the operating wavelength, and a dielectric constant epsilon r. Assuming that the polarization induced in the sphere is the same as the polarization that would be induced by a uniform static electric field, EI, given by P, the polarization vector P equal to epsilon naught multiplied by epsilon r minus 1 multiplied by the incident electric field intensity of Z directed in the Z direction, is given by 3 epsilon naught epsilon r minus 1 over epsilon r plus 2. This you obtain from the electrostatics in third year when you are dealing with dielectrics and you are looking at a spherical, dielectric object, and you are measuring that, and it's given by what you call the Clausius-Mossotti equation for dielectrics. So determine A, the backscatter cross section of the sphere, B, the backscatter cross section of a spherical raindrop of diameter 3 millimeters at 15 gigahertz, assuming that water has a dielectric constant of 55 at this frequency. This is what I was talking about, the application of the backscattering in meteorology. You are trying to determine where there is a storm using electromagnetic waves. So the polarization vector P is a constant within the sphere, and therefore we can write that the total dipole moment is going to be given by the P equal to 4 by 3 pi r cubed multiplied by pi. Remember, P is a polarization vector, or the dipole moment density, or the number of dipole moments per unit volume. And therefore, to get the dipole moments, we multiply the P multiplied by the actual value of the volume of the sphere that we are dealing with, and we get a value of that nature. Now, the time average scattered power density is going to be given by PS into the magnitude of that all squared. I've forgotten the square here. It should be ES squared, where ES is, of course, the electric field in the received wave at the receiver. So the time average incident power density is therefore going to be given by a half 1 over n. I've left up a half here of EI all squared. Hence, you can see that the backscatter is just going to be given by 4 pi, the radius of the sphere or the scattering object multiplied by its electrical radius, all raised to 4 at epsilon r minus 1 or epsilon r plus 2 all squared. So at 15 gigahertz, then we see that the wavelength is just going to be about 20 millimeters, and the radius is about 1.5 millimeter. And this gives us a value of much smaller than lambda. That is, if we were to take that over that, we'll see that this one is more than 20 times smaller than the wavelength, and therefore we can use our electrical engineering intuition or feeling of fingertip feelings that can always be ignored. So thus, we see that the backscatter cross section is just going to be given by 1.25 millimeter square, and that divided by the surface area or the cross-section area of a sphere, we get a value of 0.177. So in practice, when calculating the backscatter cross-section of water, this will require knowledge of 1, the size of the raindrops, 2, the rate of rainfall, and the equivalent spherical raindrop, because we know that the raindrops are rarely spherical and they have this kind of, I don't know whether you have heard of the concept teardrop. They will be a little bit elongated on one side because of gravity and so forth. So in transmit-receive systems, we can have what we call monostatic detection, where the same antenna is used to transmit and to receive the echo in a time-shared fashion. That is, we'll switch the antenna mode, operating mode, to transmit in a given time value. Then you'll switch off the transmission power and then wait for the returning echo. That is called monostatic detection. Or you could have bistatic detection, where you are transmitting and receiving at the same time, because you are using different antennas to transmit and to receive the radiation. So a transmit-receive system is called a radio detection and ranging, or radar system, if it is used to detect objects in space. It will be called a communication link when you are transmitting signals between two spatially separated points, such like the micro relay links that we have for the telecom companies. So measurement of the elapsed time delta t between the transmitted and the received pulses will determine the range of the object that is returning that echo R. And this is usually given as the delta t equal to the two-way path, that is the one for going to the object and one for return to the same position where you are measuring, and divided by the speed of light in the medium intervening between the two objects, that is the receiver and the object returning the echo. So if the transmission path between the transmitting and the receiving antenna is near the Earth's surface, then we have to take into consideration the effect of a conducting Earth, because the conducting Earth will also cause reflections. So we consider a communication system between two stations, that is station A and station B. Say, for example, your mobile phone and the base station that is transmitting the energy towards your mobile phone. So they are spaced at distance r apart, and they are using antennas with effective apertures the E of A and effective aperture of B respectively. So if we take PRX and PTX as the received and transmitted time average power respectively, then we see that the ratio of the received power over the transmitted power is going to be given by what we saw before as the effective aperture of the receiving antenna B over 4 pi r squared multiplied by the directive gain of the transmitting antenna A. And this gives us a value of EA multiplied by B over 4 pi r squared and multiplied by the directive gain of A defined by its universal constant 4 pi by lambda squared and multiplied by E effective aperture A. Remember, we have already seen how we can get the value of the effective aperture of the antenna A. Or in other words, that ratio of the received power to transmitted power is going to be given by the effective power of the transmitting antenna divided by the lambda squared, that is the wavelength squared, multiplied by the effective aperture of antenna B divided by the intervening radius squared, or distance squared. And this expression is usually called the Friis transmission formula, and it's always useful in determining the link budget of a communication system. For those of us who will be working with Safaricom, Airtel, or the likes, we'll be needing to, if we are designing a radio link, we have to take this into consideration. That is, what is the minimum distance or the maximum distance our transmitter can still, should we put a receiving antenna from the transmitter for us to have an effective signal. And therefore it will give you the rate at which you have to put the repeater stations. So the phase transmission formula can be expressed in terms of the directive gains of the antenna as well as given by that, where we have just removed the values of the effective apertures and replaced them with their definition using the directive gains of the antenna. And we see that they're universal vector there. And we can see that because lambda is a very small value compared to r, that is, we could have put this lambda and r all squared, then you can see that this is going to be a very small value, okay? So the ratio is going to be small as well. So this has assumed that the received power has been received by a matched load, and the power dissipation in the antenna has also been assumed to be negligible. Remember, an antenna, even the base stations, you have seen they are usually mounted on pylons, which are usually made of conductive material for the strength because of the wind speed, wind loads that we would have on the antenna. And therefore, those supporting structures will also be absorbing some of the powers incident on the antenna and therefore being dissipated. And therefore, what we are saying is that the antenna system power dissipation is small. So the received power then increases with increasing frequency, but the transmitted power will be limited by the technology available at the time of design, the minimum detectable power above the noise floor. Remember that the noise floor in many cases will be dependent on what we have, that is the background radiations that we have. So they'll determine how much power you must send to the antenna, must be received at the antenna above that background electromagnetic signal for you to detect that signal itself, the desired signal. And while the expression for the directive gain suggests that the received power will increase with the decreasing frequency, we must recall that the directive gain will be decreasing with increasing wavelength as well. So consider a monostatic radar system that is utilizing short radio pulses with a harmonic time dependence. That is, we are switching on a sinusoidal generator on and off. It's what you call in digital communication system the on-off keying. Okay. So for amplitude shift keying or something like that, I think. So we have for a transmitted power PTX, the power density PT at the target to be given by PT equal to the transmitted power divided by the surface area of the sphere enclosing the transmitter at the target and multiplied by its directive gain, okay, in the direction of the target. So if the target is assumed an isotropic scatterer, that is, it scattered the received power in all directions, the equivalent scattered power is just going to be given by the effective, that is the backscatter aperture of the scatterer multiplied by the receiver, by the power PT at the target. And hence, at the antenna, the scattered power density is going to be given by PS equal to sigma BS and multiplied by PT divided by 4 pi r squared, where this is now the surface area of the sphere that encloses the scatterer that is centered at the scatterer. And then if the effective aperture of the antenna is given by AE, then the received power is going to be given by the effective antenna of the aperture of the antenna multiplied by the backscatter cross section multiplied by the power available, that is average power available from the scatterer, and we get a value of that nature. And therefore, we can get the received power to transmit power given by the backscatter cross section multiplied by lambda squared by 4 pi and multiplied by the directive gain of the antenna divided by each surface area all square, the surface area of the sphere enclosing, enclosing the antenna all square. So this expression is what is called the radar equation, and can be recast in the form the receive to transmit power ratio given by sigma, that is the backscatter cross section divided by 4 pi multiplied by the effective aperture of the antenna over the wavelength of the signal of the operating wavelength multiplied by the intervening distance squared all squared. Remember, we are using the antenna to both transmit and receive, to transmit the incident energy and to receive the scattered power from the scatterer. That is why we was talking about a monostatic system, radar detection system. So an example then. The input power to the antenna of a radar system operated at 3 gigahertz is 50 kilowatt. The antenna has an effective aperture of 4 meters square and a radiation efficiency of about 90%. If the minimum detectable signal power in this system is 1.5 picowatt, that is, the received power must be above 1.5 picowatt for it to be detected, and the power reflection coefficient of the antenna in the receiving mode is 0.05, determine the maximum usable range of the radar system for detecting a target with a backscatter cross section of 1 meter square. So we have that the operating wavelength is 0.1 meters, and the effective aperture of the antenna is 4 meters square, and the backscatter cross section is 1 meter square. This is information that we already have given in the equation. Another thing we have is that we can see that the transmitted power to the scatterer is just 90% of the 50 kilowatts of the antenna, and we get a value of 45 kilowatt. And therefore, the received antenna is going to be given by the 1.5 picowatt multiplied by 1 over 1 minus 0.05, where this is, of course, the reflection. Remember, we are not squaring this because we are talking about the power scatter reflection coefficient, which is the modulus of gamma squared, where gamma, of course, is the reflection coefficient for the fields themselves. So, and this will give us a value of 1.58 picowatt. That is, for us to detect the target, we must receive 1.58 picowatt, okay, rather than the 1.5. The 1.5 is the minimum we can get, and that will be at the noise floor. That is, it's the same power as the background power, and therefore we can't know whether the object is there or not. It's more like when you are looking at a TV with a bad antenna, where you see the image is all lost in the snow that is appearing on the screen, and therefore the picture should increase above that snow level for you to be able to see a semblance of that your favorite Manu player playing football on TV. So this is the amount that we must receive at the receiver for us to detect the object. And therefore, we use this value and this value to compute the longest distance that this system can be used to detect that object. And this, once we plug those things in here, we get a value of 43.6 kilometers. Therefore, if you are going to use this, the object has to be 43.6 kilometers away from you. Now imagine you are trying to detect a jet fighter that is moving at, say, 0.5 Mach. That is 0.5 times the speed of sound in air, which is about 330, let's say 330 kilometers per second. Okay? Then 43.6 kilometers will suddenly become like, not a range at all. You can't, the object will, or the fighter will already be with you before you even detect it, so to speak. So, in a satellite in a geostationary orbit, from the is an orbit above the Earth's surface, where the satellite will appear stationary with respect to the Earth's surface. That it's rotating at the same speed as the Earth is rotating about its axis. And therefore, it will appear to be stationary from when we observe it from Earth. So, a geostationary orbit communication system travels in the orbits in the Earth's equatorial plane with the same rotational speed period around the Earth as the Earth's axial rotation. So a geosynchronous orbit has a radius of about 43,200 kilometers, and with the Earth's radius of about 6,380 kilometers, the geostationary satellite will be traveling at a speed of about 36,000 kilometers. Will be traveling at about 36,000 kilometers above the Earth's surface. So, signals are beamed from the Earth to the satellite using a high-gain antenna, where they are amplified after reception and then rebeamed back to the Earth, to an Earth station like the one we have at Longonot, at a different frequency. That is, the uplink frequency is different from the downlink frequency as well. So 3 satellites at a geostationary orbit can cover the entire Earth except at the poles. So a communication system near the Earth's surface, where we are assuming that the Earth is flat, would take the form as shown below. That is, the Earth's surface is assumed to be flat. We have an antenna here and another antenna at a higher height, H2, and this is at a height H1 above the Earth's surface. So we have a direct wave that will be received at B, traveling from A to B directly. But we can also have another one that would be transmitted down towards the Earth's surface. It will impinge on the Earth's surface as a point C and be reflected at equal angle, that is, angle of incident is equal to angle of reflection, and it will arrive at B through the path R prime. So it will give rise to an electric field in the theta R direction and in the theta D direction, where D is that value. But the reflected wave can be assumed to be coming directly from an image antenna at a distance H1 below the Earth's surface, okay, and therefore at a different kind of intervening distance from there. That is, using the method of virtual images, we can therefore remove the Earth's surface and use the 2 values there without the Earth's surface, but increasing that distance there. So the field E at B will therefore be the superposition of the electric field arriving by the direct path, and we shall call it this E theta D, and this is usually referred to as a sky wave. Then we have a wave reflected at C, which will give E theta R, and this is usually referred to as the ground wave. And hence, the E theta at B is going to be given by the direct electric field plus the reflected electric field, or the electric field due to the reflected wave. And where the amplitudes are given by a constant K multiplied by the propagation factor, or the phase factor, phase shift, and multiplied by sine theta. And for the reflected wave is of course given by that value, where that is the phase shift due to the distances, and multiplied by sine theta. And K is of course the function we had when we were looking at a dipole kind of function. Here we are using an electric dipole to give us that value. So using the method of virtual image sources, the effects of an assumed perfectly conducting earth can be accounted for. And therefore, in general, the direct electric field and the reflect electric field will not be parallel, and therefore, when D is much larger than the heights above the Earth's surface for the antennas, we can write that E theta is just going to be in the theta direction, multiplied by that constant which we got there, that is the amplitude constant, multiplied by the phase shift, and sine theta, and the antenna antenna function, that is the function factor for the antenna, where the f of r is just given by 1 plus exponent of minus jk times the path difference between the direct wave and the ground wave. And we have that r is just going to be given by that, by the rule of cosines. We get a value of d plus h1 minus h2 by 2 squared. That is the difference in hertz square divided by the d, where the d is the distance in the separating distance between antenna A and B, and r prime is just going to be given by that value, which is approximately the heights added, all squared and divided by that value. And hence, when we do the r prime minus r, we get a value of h1 plus h2 all squared by 2d minus h1 minus h2 squared by 2d, and we get a value of twice h1, h2 divided by d. Or, in other words, the f of r is going to be given by 1 plus the exponent of minus twice k h1 hd. That is the product of the antenna heights above the earth divided by their separating distance. And this is the same as the factor we obtained for a 2-element array. We can express f of r in the form of that nature. That is where we are subtracting out 1. Okay, let me show. That is, we can get one of the exponent here. We factor it out, and we get now a better looking value of that value, the half, multiplied by that expression. And we see that this is the expression, the Euler's formula for the cosine of k h1 h2 by d. And therefore, we have used it here as twice exponent of minus jk h1 h2 by d, and the cosine of k h1 h2 by d. Or in other words, we can get the modulus as simply twice multiplied by the cosine of k h1 h2 by d, or just when we use the values of k as twice pi by lambda, we get that to the expression there. So if h1 is a constant, the field at the receiver will exhibit nulls and maxima as h by 2, h2 by d is varied. That is, as we vary the height of the antenna B above ground, okay, and that ratio with respect to the separating distance, as we vary it, we'll start to get null points, or we'll get where the reception is maximum. And that's then you start seeing these issues where we have blind spots in the communication links. So f of r is called the path gain factor, and will be varying from 0 to 2 as the h by 2, that is k, h1, h2 by d is varied from 0 to pi, so to speak. And that brings us to the end of that section. So I'll give you a 5-minute break. We meet at 10:22. But if there are any questions, you can ask them now. Before we break, then we can have a break. Do you have any questions? Let me see. Well, no questions. So then I'll therefore say that since we are all silent today, we have decided to give you the silent treatment. Well, I'll therefore give you the 5-minute break. Let's meet after the 5, that is 10:22, and we can continue from there. Okay?
Okay.
Okay.
So we shall now continue and look at the different types of antennas that we have. This one is just to show you the kind of antennas antenna systems that can be done. We have seen representative ones, that is the thin linear antennas. We have looked at the Hertzian dipole. We have looked also at the magnetic loop. And of course, we have looked at the quarter or the half lambda dipole. And now we want to show what are the practical antenna types that we have out there, which you can always consider when you are trying to design a communication system or a radiation system and such kind of applications in your daily work as an electrical engineer after you graduate. So we have antennas that are called aperture antennas, and these are just holes cut in conducting plates and the likes. So we can say that electromagnetic radiation can be, in many cases, viewed as emanating from an opening in a conducting enclosure, such as slots, a horn, or a reflector. Well, it's unfortunate that you are not resident or we are not taking this course on campus. Otherwise, we usually show how these horn antennas look like when from the practical antennas that we have in the labs. So an approximate analysis for aperture antennas assumes that the electric and magnetic field intensities will exist only in the aperture region. So a slot antenna, okay, in a slot antenna, the dominant mode is, of course, the waveguide mode, which is the TE10 mode, and the field will usually be assumed to be a half sinusoid over the length of the slot, with its maximum at the center of that slot, where we are assuming that that's where we connect our, generating function or the generator. So in a horn antenna, this can be assumed to be a rectangular waveguide or a circular waveguide which has been allowed to flare out into a funnel-like kind of structure. The aperture field is derived from the waveguide mode that would be propagating into a horn that has been assumed to be of infinite extent. That is, it tapers out from the neck of the horn all the way to infinity. And therefore, at some given length, of course, it will be matched to the free space, and therefore the efficiency of radiation will be maximum at that particular time. So aperture fields in a reflector or a lens, a reflector is, of course, like the satellite dishes that you see over the, the DSTV dishes and the likes, okay? Or lens antennas are determined from the reflection of refracted rays emanating from the primary field by methods which are equal to those of the geometrical optics, which we looked at last semester. So we are going to consider a large conducting sheet of metal in which we have cut out a slot of that nature there. And this is oriented in the x direction, and we are trying to look at a field point at a distance r from a small element of surface on the slot itself, okay, where that is the point we are dealing with, and we are looking at the field that will be appearing at that point. So the shaded part is the metal, and the white part is where we have cut out the slot itself. So for the TE10 mode excitation, the field in the plane aperture is approximately linearly polarized, and results obtained deviate only little from those of the geometrical optics solutions. So with a nearly uniform phase over the aperture, then the far field at P is a special 2D Fourier integral of the distribution in the aperture. So let the electric field intensity distribution in the aperture be linearly polarized in the x direction and has no variation in phase. That is, everywhere it's in phase over the length of that aperture. So we can therefore write that the electric field is going to be given by X multiplied by E of A. So for an aperture, okay, dimension, or for aperture dimensions that are much larger than the operating wavelength, then nearly all the electromagnetic energy radiated will be confined to a very small region about the z-axis. Okay, and this is what we call the paraxial approximation. And hence, the paraxial field is just going to be given by E of P equal to the x cap multiplied by E of P, where E of P is just given by the integral over the aperture of the field in the aperture, okay, at a given point x prime y prime exponent of the minus of j k r prime, where r prime is of course the distance of the field point from the element of area that is contributing to the electric field at the field point, and multiplied by, of course, the surface area, or the element of surface area dx prime multiplied by dy prime. So when kr is much larger than unity, then we can write that r will be approximately r naught minus x cap x. This x cap should not be there, so we should be getting just the values of that. Yeah, that's correct. That is the vector, the position vector of the element of area multiplied by the position, the unit vectors in the spherical coordinate system. Or in other words, you can get that r prime is just going to be given by r. I think this should be r prime equal to r minus, where r is of course the distance of the field point from the center of the aperture. Let's see, this is what I mean. Those symbols are a bit done. That is the r I'm talking about. So this is the r not appearing in the expression, and that is the r prime. So I'll be correcting that for you before casting this to you. So we'll get a value of r prime approximately given by r minus that dot product there, which you can see as that value there. Hence, the E of P is just going to be given by the J over lambda r multiplied by the exponent of minus j k r and multiplied by the element factor, which we are going to have as f theta and phi equal to the integral over the aperture of the electric field multiplied by those values there. And we call it the pattern function of that aperture. Now, if you look at this, it looks like a Fourier transform in the spatial dimension, not in the spatial case. If you were to replace the x prime and y prime with time, then you get a Fourier transform in the frequency domain and so on. So here we are dealing with what we call the spatial Fourier transforms. So that's the field distribution in the aperture, and the pattern functions are Fourier transforms of each other. So for a rectangular aperture of dimensions a by b, assuming separable fields such that the E of A, that is the aperture, the field in the aperture at x prime, y prime can be written as a function of x prime alone and a function of y prime alone, then we can write that in this, the Fourier transform is going to be given by f of theta by phi equal to the integral from minus a by 2 to a by 2, where a, of course, is the length, and multiplied by the f of x prime, exponent of minus jk x prime sine theta cos phi, and dx, and a component in the y direction. So of interest is the pattern or in the principal planes of radiation. And hence, in the xz plane at phi equal to 0, we have that fxz of theta is just going to be given by that expression, okay? Or we can write it as cy, okay? Integral multiplied by the integral of the f of x, where cy is a constant where we are integrated with respect to that value there. In the YZ plane, at phi equal to pi by 2, we have a similar expression, and we get a function cx, which is just the integral of that value there, and we get a value of that nature. So we have the maximum radiation intensity, Kmax, given by 1 over twice the intrinsic impedance multiplied by the distance square and the magnitude of the field at P maximum, and we get a value of that, which is just the integral of the electric field in the aperture all squared. And the total radiated power is therefore PR multiplied by that value there. So hence, the directivity of the rectangular aperture will be given by D equal to 4 pi Kmax by PR, where remember PR is the average power, assuming that it's being radiated equally in all directions, and we get a value of 4 pi by lambda 2 equal to that integral there squared divided by the integral of the square of the magnitude of the aperture electric field. And over that value, the prime here has been left out, typographical error there. So for constant amplitude in the aperture, that is uniform aperture field distribution, the directive gain and the directivity will be maximum, and it will be equal to the product of 4 pi by lambda squared and multiplied by the physical cross-section area of that aperture. So example 1 then. And for an A by B rectangular aperture with a uniform field distribution, determine the pattern function of a principal plane, and B, the half power beam width, and C, the location of the first nulls, and D, the level of the first side lobes. So we see that EA is normalized to unity in the aperture, and in the XYZ plane, we therefore have that fxz is given by that value B and multiplied by that, and we get a value of AB divided by sine phi by psi, that is the sink of psi, and we get a value of psi, where psi is just pi A by lambda multiplied by sine theta. For the Y pattern, we have the same with the Cx given by the length or the width of the aperture. And we note that the pattern function is therefore similar to the array factor of a uniform array for psi when psi is small. So the half power points are obtained by setting the sine of psi 1 by at the half power point divided by the psi at half power point, that being equal to 1 over root 2 in the usual definition of half power points. Or, in other words, the psi at the half power point is going to be given by pi A by lambda multiplied by the sine at the half power of theta at half power point, or a value of 0.442 multiplied by lambda by A. So when the aperture is sufficiently large, then sine theta 1 by 2 is going to be approximately theta by 2, because theta at half power point is going to be very, very small, and we have 2 theta 1 at the half power point of approximately 0.8884 lambda by 2 by A rather. So the first null will therefore occur at psi 01, which is given by that value, which is lambda by A, and the first side lobes will be located at psi 1, such that the derivative of the sink function at psi by 1 is equal to 0. We are not going to differentiate it twice to ascertain that that one is really a maximum and not a minimum. So we are going to say that the tangent of psi 1 is approximately psi 1, which is equal to plus or minus 1 by 4,3 pi. So hence, we can get that sine psi by 1 by psi 1 is equal to that value there of about 0.217. So when we refer this to unity at psi equal to 0, then the first side lobes will be 20 log 1 base 10 of 1 by 0.217, or 13.3 pp below the level of the major lobe. So example 2. A linearly polarized uniform electric field with an aperture field EA exists in a circular aperture of radius B cut into a conducting plane at Z equal to 0. If B, the radius of the cut or the aperture, is much smaller than the operating wavelength, derive an expression for the far field, and B, determine the width of the main lobe between the fasteners. And because of the circular symmetry of the aperture, we can use polar coordinates where we let x prime be equal to the radius of the aperture multiplied by the cosine of the azimuthal angle, and y to be r prime multiplied by the sine of theta, phi prime, okay, the azimuthal angle. And therefore, we can see that x prime, cos prime, and phi prime plus that is going to be given by those values, which is just the same as r prime, the cosine of the difference between phi and the phi prime. That is phi measured at the field point and phi measured at the source point. And therefore, when you get the pattern function as the integral over the radius and over the azimuthal angle, we get that value, and we get a value of that nature where we are using the Bessel function of the first kind and order 0 for that particular case. And then we can see that this value is just going to be, I've used an identity for the integral, so we'll get a value of J1, KB sine theta, or KB sine theta. It looks just like the one we had for the rectangular plane, only we were using the trigonometric values rather than the Bessel functions. And hence, the field at the field point is just going to be given by that value, where U has been described as KB sine theta, which is equal to twice pi b by 8 lambda multiplied by the sine theta. So the first nulls will occur at the first zero of the J1, say U11 of about 3.832. If you recall the tables like I gave before when we were looking at the circular waveguides, we had the roots of the Bessel function of the first kind and their derivatives as well. We showed where the roots would be. And therefore, this will correspond to an angle of theta 1 equal to the arc sine of that value divided by twice pi b, and we get a value of 1.22 lambda by d, where d is, of course, the diameter of the aperture. And hence, the width of the main lobe between the first nulls will be given by the 2 theta 1 equal to 2 times 2.44 lambda by d. And we see that the beam, okay, will be wider for a circular aperture antenna, okay, than a rectangular one. And remember, if you recall, the beam width was proportional to the longest, okay, to the largest dimension of the aperture. Here for the circular, of course, is the diameter, and for the rectangular wave aperture was the width, which was A greater than the height B, okay? But if you look at many of your satellite dishes, the the DSTV dishes, you can see that the horn antenna that is feeding or that is beaming or illuminating the circular disc or the circular reflector or spherical reflector is usually of circular, of circular form. We don't usually use the rectangular one, and this is just because of the ease of manufacture, so to speak. So the level of the first side lobes for the circular aperture is about 0.13, which is 17.7 dB below the main lobe, and therefore it's better than that for the circular waveguide, and therefore it gives us a value or a reason why most of the antennas will be using the circular horn antennas rather than the square ones, because of structural issues and also the manufacture issues. And now we have the differences between the side lobe levels. And we note the following identity, that the integral of a function exponent of Ju cos phi, the phi is just given by twice pi J naught, that is the Bessel function of the first kind of u, and the integral of u, ju du is just simply j1 of u. This is just to help us do the calculations if we are given a problem like that to solve. So some other types of antennas that are there is that when the wavelength or the length of the antenna is much larger than a wavelength, then we can start seeing that that antenna will support a traveling wave, just like in a transmission line. So if a linear antenna is several wavelengths long and then properly terminated, that is, we can terminate it in its characteristic impedance, then the antenna will behave like a transmission line that is terminated in its characteristic impedance. So we consider a section of wire of length L comparable to a wavelength which is placed above the ground plane. And at the far end, we terminate it in an impedance of, say, R, which I'm calling here a terminating impedance. So we are connecting the generator between the earth surface or the ground plane and the line, the length of line there, that is of length L. So we'll excite a traveling wave in that direction, which will travel to the terminating end and be absorbed. So that is, we are not having any reflections in there. But at a field point P, a distance r from that antenna, the axis of the line, what would be the electric field, or what would be the fields at that point? So the equivalent transmission line is appropriately terminated such that we have no reflected waves existing on the line. So the line current is then a traveling wave with a distribution that will be given by I of z equal to I naught exponent of minus j kz, where the z is measured along the line, just like we had for the transmission line. So if we ignore the effects of the nearby ground, because the line is not very far from the ground, the far field electric field intensity will then have a form that J multiplied by the impedance, intrinsic impedance, multiplied by the propagation constant over 4 pi r, the sine theta exponent of minus j k r, and multiplied by the distribution of that current, where the kz multiplied by cos theta is the phase shift over the line dz. And we get a value of that nature, where we have used that equation there in terms of the components, so to speak. What did I do here? That is, I've done that. What did I do? We have minus jkz there. I think this one should be removed from that position there to put it in there. Or in other words, oh yeah, yeah, this is correct. It's just to get it out there, and we multiply that in through, so that we can get that minus jkz representing that, and multiply by the cosine of theta. But I'll check this one properly for you before I send the corrected version. So E theta will therefore be given by that expression multiplied by the pattern factor f theta, where f theta is of course given by the sine theta of 1 minus cos theta, sine k of L by 2 into 1 minus cos theta. So the pattern function of the structure is not symmetrical about the theta equal to pi by 2 plane, like in the standing wave ratio with antennas, the resonant antennas such as the lambda by 2 dipole. Okay, the values are not symmetrical about that point. Okay, and the main lobe will be tilting in the direction of the current wave propagation on the line, and the tilt angle will be increasing with increasing line length, and the side lobes will also be very large. So we can account for the effects of the ground plane using the method of virtual image sources by reflecting that current or that line into the ground, and we get another line at the bottom, and now we have a transmission line, okay, with those two generators feeding it, and of course the two distances, that is the two terminating radius impedances at the end of the line. So we therefore note that this is therefore an array of two traveling wave antennas, antenna elements that are carrying equal but oppositely directed currents as shown in the diagram. So the principle of pattern multiplication will then yield the pattern function of f theta multiplied by the cosine of psi by 2, where the phase of the current is of course given by alpha equal to pi because they are oppositely directed for this particular case. Thus the cosine psi by 2 modulus is just the cosine of k multiplied by h, where h is the distance or the height of the line over the ground, multiplied by sine theta cos phi plus pi by 2, and we get a value of that multiplied by the sine. There is something missing there. So the spatial field distribution is therefore will be of this particular nature. This is the direction of propagation of the current, which is taken at 0 degrees. And you see that the lobes, the main lobes are on either side of the line, and they are directed at that direction there. The numbers here should not, it's for a particular kind of excitation. It's not that they are generally pointed in the 20 degree, 340 degree direction, okay, or on opposite side of the line, okay, that is parallel to the ground, so to speak. So then another one is what we call the helical antenna. This was designed or invented by Krauss, okay, when he was working at Ohio, and it's very famous because it was the line or the antenna that actually received the first inkling of extraterrestrial occurrences. The signal usually referred to as the wow signal, which lasted for about 72 seconds. It came from the direction of the constellation Sagittarius, but it has never been received again. But it had semblances of intelligence, but since it has never been repeated, the issue has not been resolved to this date. So it's a linear antenna or a small current loop that radiates waves polarized in a given direction. And therefore, reception of such a wave will then require that the receiving antenna be oriented parallel to the electric field of the incident wave. In some cases, the polarization of the wave may not be known a priori. Okay, that is, we won't know it, especially in satellite communication. We know that satellites are above the Earth, and usually they'll be above the atmosphere. Therefore, they are beyond the ionosphere. And because the Earth has a magnetic field by itself surrounding it, then a field or a wave being sent down to Earth from the satellite will interact with this magnetic field, and the electric field polarization of the wave will be rotated. And this is usually referred to as Faraday's rotation. The direction and the amount of rotation is not known, it's random because the conductivity and the magnetic interaction with the Earth's magnetic field is usually a random process, and therefore the wave that will be arriving on Earth will not be known which polarization it has. And therefore, most of the times is that you'll send down the field or the wave sent down from the satellite will have a circular polarization, and then at the ground we can use a linearly polarized antenna, and we'll get at least some kind of field induced in our whatever. But even if the polarization is changed by the ionosphere, the polarization at the receiving antenna will not be that much affected because of the circular polarization we are talking about. So the radiation from the antenna on the satellite must pass through the ionosphere, where we have said it will suffer Faraday rotation that will depend on the free electron concentration in the plasma of the ionosphere and the intensity of the Earth's magnetic field. And the path of propagation, how is it passing through the ionosphere? If it spends more time in the ionosphere, the rotation is much larger than when the radiation is normal to the ionosphere itself. So such situations then will require an antenna with circular polarization because they intercept the radiation polarized in any direction that is not normal to the plane of the circle of polarization. So recall that a circularly polarized wave can be expressed as a superposition of two linearly polarized waves like we saw in the last semester. So an antenna with just this characteristic is what we call the turnstile antenna that consists of two cross-polarized dipole elements excited by a quadrature phase current of equal amplitude to produce circular polarization. So another popular antenna of this particular nature to produce circular polarized wave is what we call a helical antenna, as shown below. It's just more like a coil, okay, an inductor coil or a spring coil, and it's fed by a coaxial line, and this would be a vertical helical antenna. And we can actually spread this in this form where S is called the pitch, that is the distance between the coils, and each of the coils is done like that. So we are just looking at this helical antenna as a combination of magnetic dipoles and elemental electric dipoles. And therefore the E-plane radiation pattern will just be the same as we had before for the for the dipole antenna that we looked at. So depending on the dimension of the helix, the antenna has two modes of operation. One, we can have a broadside radiation pattern similar to that of an elemental electric dipole when the dimensions are much smaller than the operating wavelength. That is the normal mode of operation of these antennas. Then we can have an end-fire radiation pattern when the dimensions, that is the circumference and the turn spacings, are comparable to the operating wavelength. And this will be called the axial mode. So in analysis or in analyzing antenna performance operated in this mode, that is the axial mode, then we make two assumptions. One, that the helix can be replaced by a combination of elemental magnetic dipoles separated by elemental electric dipoles, as we have shown in that diagram. And the current along the helix is then assumed to be uniform in both amplitude and phase. So in the far field, for an N-turn helical antenna, it will be a superposition of the contributions from all the elemental magnetic and electric dipoles that form the helix. And hence, the E field is going to be given by an E theta coming from the electric dipole plus an E phi coming from the magnetic dipole antenna. And we get a value of that value there multiplied by that S, where S is the pitch of the helix and pi b squared is the area of the loop. So we see that the theta and phi components are in both time and spatial quadrature phase, and therefore result in elliptically polarized radiated waves when they are not of equal amplitude. So for circular polarization, we then require that the S be equal to K multiplied by the area of the loop, or rather the radius of the loop must be equal to 1 by pi multiplied by the square root of S multiplied by that is the pitch of the helix multiplied by the operating frequency or wavelength and divided by 2. So the maximum radiation will be broadside with a donut pattern of the dipole antenna of 0 inner diameter, and the radiation efficiency and effective gain are usually very low, and the antenna is rarely operated in the broadside mode. So in the axial mode, the radiation is end fire with the radiation elliptically polarized in that direction, and you see that it's directed in one direction there with very small back radiation. So another one which is very common is what we call the Yagi-Uda array antenna. It's a passive array that is shown here, and it's used for TV and also many communication links, especially in the police lines. I'm sure you have seen one like this at the police station, central police station. In the homes, of course, this element will be folded So you have a folded line, which is we usually call the active antenna or the active element. These are shorter than the active element, and therefore they are used as focusing the radiation coming from this end onto the active antenna when the antenna is used in receiving. But when it's used in transmitting, they are used to focus the beam towards that direction. This element here is longer than the active antenna or the active element, and it's used to reflect any backward radiation from the active antenna element backwards. It's reflected forward, and it's placed at a distance such that when the field arrives at this point, it's actually constructive interference, and the field therefore will be directed in one direction. So this Yagi is very popular, and I'm sure many of us have seen it because it's almost everywhere. Even the Gikomba guys usually design such kind of antennas. So in transmitting mode, the Yagi is an array of linear antennas with only one element excited, and we call it the active element. In the receiving mode, the electromagnetic wave impinges on all the elements, but it's only collected from the active element. And the feed structure of the antenna is usually simple, and this accounts for its popularity in the practical arena. And since all the elements of the array are coupled, the current distribution on the back element will depend on the length and the spacing of all of the other elements. So in practice, it is found that there is little advantage in using more than one reflector. That is, you want to capture some that leaked through, but the directivity of the antenna will be improving by increasing the number of directors. But this makes the antenna very long. So the radiation is usually end fire, with the main lobe pointing away from the reflector in that form. That is, a reflector will be on this other end, okay, and it has a very small value. So what I was saying, the front to back ratio was the ratio of the amplitude or the height or the level of that main lobe to the level of the back lobe. So a well-designed Yagi antenna would therefore must have a high directivity or a narrow beam width. Two, the reason why is because most of the time places where the Yagi is used is in say around the estates, and the incident waves will be scattered or will be reflected multiple times by the buildings and so forth, and you don't want to receive from the back of the antenna, okay? And therefore you can only get the field that is coming from the front, so to speak, and therefore it reduces interference of the received signal. Then the side lobe must be low, and it must have a high front to back ratio. That is, the level of the front directed lobe to the back directed lobe must be high. So a typical 6-element design using elements with a radius of A equal to 0.00336, like this. That is, the natural log of lambda by 2A is about 5, with 4 equal length, equispaced directors, would then have a performance parameters of the following form. Twice the length of the first director, the second director, the third, the fourth, and the fifth will give you that value. So this is the reflector. So it has a value of 0.510 lambda. The second one has a value of 0.490 lambda. That is the active element. And this active element has been deliberately made smaller than half lambda, like we said before, because you remember the endpoints will introduce some capacitance. And we must make the length shorter than half a lambda so that we can introduce inductive effect to tune out the fringing effects of at the ends of the antenna dipole. Okay, that's why we are using a smaller value of the length than half lambda. And those are the directors which have been assumed to have the same length. So B1 and 2, B21 is the separation, and we get a value of 0.250 quarter lambda for the two, for the director, that is the active element and the director and the reflector, and then 3.10 lambda for the rest of the others. And the pattern parameters would then be a half beam width of 45 degrees, a directivity of 7.54 or 8.77 dB, referred to a half-wave dipole, and the first side lobe will be minus 7.2 dB below the main lobe, and the front to back ratio is about 9.52 dB. This has not been optimized, and usually when you are designing, you want to optimize for maximum performance or optimal performance, and you see that the directivity here is about 0.164 dBi. So uniformly spaced directors of equal length do not yield an optimal array, and therefore when you design it for optimal performance, then you'll have the same rod radii, and we use an antenna parameters of that nature where all of them have different values. We see we have cut the active element much shorter than before. We had 0.49, but now we are using 0.452 of lambda. And we see that the directivity is now improved to 13.36 or 12.58 dB, referred to a half-wave lambda dipole. A beam width of that is narrower is now 37 degrees, and we have a side lobe that is deeper, which is 10.9 for the first side lobe, and that front to back ratio of about 10.04 dB. The other one was just 9 dB, so to speak. So now what we have seen. Yes.
I'm afraid our time is up.
Oh, the time is up.
Yes.
Okay, I'll stop then at that page. That is page 38. We'll complete that next time. And this is we are just talking about the antenna type before we now go to another topic that will be slightly different. So thank you for listening to me. If there are no questions, of course, I'll do the usual. I just wish you a nice weekend, and try and stay safe. Get vaccinated if you are among the frontline workers. Okay? But stay safe, so to speak.
Okay, thank you.
So
Have a nice weekend.
Okay, thanks too. Bye.